This is the universe, or at least a portion of it. It is an intricate dance between galaxies, stars, and black holes. But behind the web of matter, there are null voids scattered throughout the cosmos. These are represented by the black dots straining the marvelous orange and purple filaments. No, these are not black holes, nor are they voids in the plenum. This is something altogether different. These are packets of dark energy. It was Albert Einstein who first suggested that there is more to these patches of nothingness than meets the eye, though he would later redact the idea of a cosmological constraint from his work. But whether he realized it or not, Einstein was on to something. Those voids are not nothingness. They contain a substance that dictates how the universe expands. But what are these mysterious forces, and how do they determine the fate of the universe? Though they appear as blips on a cosmic scale, these voids can be up to 160 million light-years across, and they make up the bulk of the substance of the universe. The matter that we can see and observe, like stars, planets, and trees, make up for less than 5% of the known universe. 25% of it is dark matter, and the remaining 70% is dark energy. Those pockets of emptiness contain dark energy. Understanding dark energy is key to understanding why the universe is expanding faster and faster, and eventually, the fate of the universe itself. The entire evolution of the cosmos is dominated by dark energy, and we know frighteningly little about the biggest player in the theater of the universe. If we can understand where dark energy comes from and how it interacts with the rest of the universe, we can come to a better idea of how the universe will end. Dark matter is very different from dark energy. Even though in everyday use, the two are used interchangeably because they are both called dark. It also makes more sense for people to put two and two together because energy and matter are linked through Einstein's equation. But dark energy and dark matter don't behave in the same way as we know normal matter and energy do. They are called dark because we can't see them, and because they are a conundrum, a mystery we have yet to fully unravel. Dark does not imply black. They are dark in the sense that they are invisible and don't emit or absorb light. Dark matter can be detected, however, as in regions where it is found in high concentrations. It tends to wrap the light that passes around it. This means that we know something exists there that can interact with gravity. Dark energy is a far greater enigma. We can't detect it or measure it in any way. The only way we have been able to define it has been through the expansion of the universe. In 1929, Edward Hubble noticed how the wavelengths of light coming from distant galaxies showed a large degree of redshift. Hubble deduced that this was because the universe itself was expanding. More recent studies have shown that the universe is expanding at an accelerated rate, so dark energy might just be some intrinsic property of space that exists in a limited capacity throughout the entire universe. But this is just speculation. So, what does dark energy have to do with the expansion of the universe? Well, as dark energy interacts with space as the universe begins expanding unprecedentedly, the force of gravity holding everything together would no longer be sufficient, and thus allowing for faster and faster expansion. So that's one explanation for dark energy. It is a cosmological constant and is necessary to structure the universe. But it is also possible that it is something else entirely. Maybe whatever is making the universe expand is working in a drastically different way from what we expect. One of the possibilities that astronomers have come up with is phantom dark energy. This form of dark energy gets stronger and stronger with time. So in a particular volume of space, the dark energy present would just grow and grow. If this were the case, then the outcome would be very apocalyptic. If dark energy gets more powerful with time, it will eventually get strong enough to rip the universe apart. The universe will expand, and the concentration of dark energy will begin to grow. Initially, this will present itself as neighboring galaxies casually drifting away from each other. Then, steadily, as the power increases, the planets will be ripped out of their orbits and pulled apart from their stars, and eventually, it will just get to the point where it is ripping everything else down to atoms. And at some point in the future, it will rip apart the entire universe. And this is what we call the Big Rip theory. Since our knowledge of dark energy is very limited, we can also assume that in the future, it will behave in a completely different way from the way it is now. It doesn't get more powerful, but actually it gets less powerful until it changes directions and starts to collapse into itself. So, instead of expanding the universe like it is now, it could, sometime in the future, start to pull the universe back together. Scientists for a long time have been trying to calculate when things in the cosmos would start slowing down, because it should be slowing down. The Big Bang kicked off the expansion, and since then, the gravity from all the matter in the universe was supposed to turn things around and instead pull things back together. So, there is this eternal conflict between expansion and gravity to see which one would prevail. If gravity does win the battle, then the expansion, at some point, will come to a halt and distant stars and galaxies would start to come back. We would get to see more galaxies make their way towards our own. We would see them collide with each other more frequently. The universe would begin to shrink in on itself. Now, it's not just that the universe would be getting denser and more concentrated. When the universe compresses, it would also bring together all the background radiation. And we know that there is radiation in the ends of the universe from the time of the Big Bang, from when the universe was still very hot and dense. All that radiation is still out there. And when you compress the universe, you're bringing back all that radiation to a more confined space. And it's not only the radiation from the Big Bang, it's the radiation from all the stars that have ever burnt and from all the supernovas that have exploded. Bring all that energy in one place, and you would essentially be heading towards reverse Big Bang. At some point, when you concentrate all that energy, it would be enough to ignite the surfaces of stars and cause them to burn from outside in. It's like nuclear fusion on a planetary level, and by that point, the universe will collapse in on itself and cease to exist. That is the Big Crunch theory. Let us not forget that all this is contingent on the fact that dark energy behaves in this way, which we don't know if it will. Dark energy is just so weird that we can't definitely discern anything about its interaction with the universe. What we do know is that whether it is the rip or the crunch, it would take place hundreds of billions of years from now. Our theories about dark matter and dark energy are just that, theories. Primordial black holes, or PBH, are believed to form due to the fluctuations in density at the early universe. PBHs are really primordial in the sense that they were formed before any astrophysical objects. At the very early stages of the universe, Stephen Hawking proposed first that these black holes can even have masses lower than the Sun, actually as low as 10 micrograms. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first signature of gravitational waves in 2015, as two black holes merged to create ripples in space-time. Since these colliding black holes were much larger than expected, many theories suggested that these black hole mergers could be primordial in nature. One of the biggest constraints on a primordial black hole's mass comes from the observation of gamma rays, as the Hawking radiation should be detected by the gamma observatories. In their latest research, the University of Miami and the European Space Agency took a deep dive into the theory of primordial black holes, exploring how they might explain the dark matter and possibly resolve other cosmological challenges. To fit in with current observational tests, they believe that primordial black holes have to fit into a certain size range. While it may seem frustrating to not know exactly how the universe will end, this does go to show that at the end of the day, we are just as clueless about the cosmos as our earliest ancestors that gazed up at the stars. Thank you guys so much for watching. If you enjoyed the video, be sure to leave a like and subscribe to the channel for more content just like this.